Hello everyone, welcome to this TYBSc MMP class. In today's lecture we are starting third chapter differential equations. Today we are going to discuss different types of differential equations, that ordinary differential equation, partial differential equations, and the terminology used in differential equation. Let us start. Chapter 3, differential equations. Students, you have already studied differential equation at SYBSc level in MMP first course. Let us revise few terms related with these differential equations. The first is variables. That changing entities are variables. The entities like pressure, temperature, then light intensity, sound intensity, which are changing with respect to space and time, are variables. And the rate of change of one variable with respect to another called derivatives. Rate of change of one variable with respect to another called derivative. If light intensity is changing with respect to time, then the change in light intensity with respect to time is mathematically represented using derivatives. Then the term differential equations. The definition is equations which give relation between variables and their derivatives. The differential equation is the mathematical equation which gives the relation between the variables and their derivatives. In physics, differential equations gives mathematical description of physical phenomena. The use of differential equation in almost all branches of physics gives the mathematical description of physical phenomena. There are two types of differential equations: ordinary differential equation and partial differential equation. Let us see one by one. Then first, ordinary differential equation. What is ordinary differential equation? Equations which involve only one independent variable. Equations which involve only one independent variable. For example, in case of simple harmonic oscillator, this x is changing with respect to time. Displacement is changing with respect to time, and the equation is m into d square x upon dt square is equal to minus kx, where k is force constant. Then here x is changing with respect to time. Then x is a dependent variable and t is a independent variable. In this equation, only one independent variable t. Therefore, this is ordinary differential equation. Second example, decay of radioactive substance. That number of particles changing with respect to time is equal to minus lambda into n, where n is the number of particles. N is the number of particles. Then this dn by dt. Then change in number of particles with respect to time. Therefore, n is a dependent variable while t is the independent variable. This equation involves only one independent variable. Therefore, this is ordinary differential equation. Then third example, series LCR circuit example. If inductance, capacitance and resistance connected in series and battery is connected across this series combination, and if we switch on the circuit, then current in the circuit change with respect to time. The changing current changing with respect to time. Then in this equation, I is the dependent variable. I is changing with respect to time. Therefore, this I is dependent variable and which is changing with respect to time. Therefore, here time is the independent variable. And this equation involves only one independent variable t. Therefore, this is ordinary differential equation. Then second type of differential equation is partial differential equations. The differential equation which involve derivative of dependent variable with respect to two or more than two independent variable. The differential equation which involve more than two or more than two independent variables are called partial differential equation. Let us see few examples. If f is a function of two independent variable, that f is a function which depends on these two independent variable x and y. If f is a function of x and y, then the Laplace's equation dabba square f upon dabba x square plus dabba square f upon dabba y square is equal to 0. Here x and y two independent variable. Then this is partial differential equation which involve two independent variable x and y. Then the first example, let us see few examples of partial differential equation. The first example is a wave equation. That wave equation, here psi is a function. It may be the amplitude. Then psi is changing with respect to space coordinate and time coordinate. Here delta square is the Laplacian operator. It may be one dimensional, two dimensional or three dimensional. Then this space and time change. That psi is changing with respect to space coordinate and time coordinate. Therefore, here if this is a three-dimensional equation, then here four independent variable x, y, z in Cartesian coordinates x, y, z, and the fourth is time. Therefore, this is partial differential equation because this equation involve more than two independent variable. Psi may be component of a electric vector or the magnetic intensity vector in electromagnetic wave, or it may be the displacement from the equilibrium position in oscillating string. For this wave equation is partial differential equation. Second example, Poisson's equation. That del square psi is equal to f function of x, y, z. Then psi, here this function psi, scalar function of coordinates. It may be the gravitational potential, which is changing with respect to space, in space, which is changing in space. Therefore, it depends, the psi is function of space coordinates, or it is electrostatic potential, or it is a temperature. The function f function of xyz is a source density. In this equation also, there are more than two or more than two independence variables. Therefore, this equation is partial differential equation. For example, in electrostatic, for region containing charges, Poisson's equation is del square psi is equal to rho upon epsilon 0. Then del square is function of space coordinate in Cartesian coordinates x, y, z. In spherical or polar coordinates rho r theta pi. In cylindrical coordinate rho pi z. Therefore, here this psi function of more than two or more than two independent variable. Therefore, this Poisson's equation is the partial differential equation. Then the third equation, Laplace's equation. If there is source free region, if source free region, then this here 0. In electrostatic example, if rho is 0, then del square psi is equal to 0. Then Poisson's equation converts to Laplace's equation. Psi may be a scalar function of coordinates. Example, gravitational potential in charged in a region containing no matter. Electrostatic potential in charge free region. In charge free region, rho is equal to 0, then del square psi is equal to 0. This Poisson's equation converts to Laplace's equation. Here del square is a Laplacian operator. In Cartesian coordinate, del square is equal to dabba square psi by dabba x square plus dabba square psi by dabba y square plus dabba square psi by dabba z square. Where psi is function of more than two independent variables x, y, z. In three-dimensional case, it is function of x, y, z. Therefore, this equation involve more than two independent variable. Therefore, this Laplace's equation is the partial differential equation. Next example, the Helmholtz equation, that del square psi plus k square psi plus minus k square psi is equal to 0. This equation appear in acoustics and electromagnetic waves. Again, here del square is function of space coordinate. It may involve two or more than two independent variable, as we have seen in Laplace's equation and in Poisson's equation. Therefore, this Helmholtz equation is also partial differential equation because psi is function of more than two independent variables. The next example is the diffusion or heat flow equation. Heat flow equation that if this psi is changing with respect to space and time coordinates, then if this is three-dimensional case, then psi is function of x, y, z and time t. Therefore, in this heat flow equation, this derivatives involved in this differential equation involves more than two independent variables. Therefore, this diffusion heat flow equation is partial differential equation. Psi may be the non-steady temperature. Non-steady means it is changing with respect to time, or concentration of diffusing substance like chemical. Alpha square is constant called diffusivity. For this equation is partial differential equation. One more example, the Schrodinger equation. A time-dependent Schrodinger equation in one dimension. In one dimensional, the Schrodinger equation. Here also psi is function of x and t, space and time. In one dimensional, one space coordinate and with respect to time. Therefore, there are two independent variables. This equation involves two independent variables x and t. Therefore, this Schrodinger's equation is also a partial differential equation. These are the few examples of partial differential equation. Next topic, the different terms which involve in differential equation, which are used while explaining the differential or while using the differential equation. The different terms used are degree, order, linearity, and homogeneity of the differential equation. Let us see one by one. First term, order of the differential equation. Order of differential equation. Order of highest derivative in the differential equation. Order of differential equation is nothing but the order of highest derivative in the differential equation. The second term involve degree of the differential equation. It is the power of highest derivative after differential equation is rationalized. That fractional power of derivative is removed. It is the power of the highest derivative in the differential equation. If the differential equation include any fractional terms, then after removing that fractional terms, the power is decided. That is, degree of the differential equation is decided. For example, in this equation, d square y upon dx square bracket cube plus 2 dy by dx plus 3x square y is equal to 0. The highest derivative, order of highest derivative is second, because here d square y upon dx square is the highest order of the derivative. Therefore, order of this differential equation is 2. Highest derivative is second order. So, order is 2. And the power of highest derivative, here highest derivative is d square y upon dx square and its power is 3. Therefore, degree of this differential equation is 3. Hence, degree is 3. Order 2, degree 3. Therefore, this second order, third degree differential equation. Next term used while explaining differential equation is linearity of the differential equation. If dependent variable and its derivative, if dependent variable and its derivative appear in the first power only, and no product term of dependent variable and its derivative occur in the differential equation, then only the differential equation is linear. Therefore, these two conditions must be satisfied. That the first condition, the derivative must be in first power. Derivative must be in first power. And the second condition, no product term of dependent variable and its derivative. If these two conditions satisfied by the differential equation, then that differential equation is linear differential equation. Let us see few examples. The first one is d square y upon dx square bracket cube plus 2 dy by dx plus 3x square y is equal to 0. Here the power is 3. Therefore, first condition is violated. That requirement is first power, but here power is 3. Therefore, this equation is non-linear. This is non-linear because of third power of d square y upon dx square. Next example, d square y upon dx square plus 2 dy by dx plus 3x square y is equal to 0. Here both conditions satisfied. All the terms having first power and no product term. All the derivatives are of first power and there is no product term of dependent because here dependent variable is y. Therefore, there is no any term which involve product of dependent variable and its derivative. Therefore, this equation is linear second order because highest derivative is of order 2. Therefore, this is linear second order differential equation. Next example, d square y upon dx square plus 3xy square is equal to 0. 3xy square is equal to 0. Here dependent variable is y, independent variable is x. Then the power of this dependent variable is 2, y square. Because of this term y square, the power is 2. Therefore, the this first condition is invalid. Therefore, this equation is non-linear because of second power of y. Then the next example, d cube y upon dx cube plus dy by dx plus y is equal to sin x. Here also power of derivatives is 1. There is no product term. Therefore, this equation is linear differential equation, linear third order. This order of the highest derivative is 3. Therefore, third order. And there is no any derivative having power more than 1. And there is no product term which involve dependent variable and its derivative, product of dependent variable and derivative. Therefore, this is linear differential equation. Next term which describe the differential equation is homogeneity of differential equation. The condition is if each term in the given differential equation contain dependent variable and or its derivative, dependent variable and its derivative or dependent variable or its derivative, the equation is homogeneous. If in any term dependent variable and or its derivative absent, the equation is inhomogeneous. Therefore, each term must contain at least the dependent variable or its derivative or both. Let us see with few example. The first example, d square y upon dx square plus 3xy square is equal to 0. Both term involve the dependent variable. Y is the dependent variable which is present in both terms. Therefore, this is homogeneous differential equation. Next example. In this example, this sin x term, there is no dependent variable because y is the dependent variable. In first three terms, if y is present, y or its derivative is present. But in this term, there is no dependent variable or its derivative. Therefore, this is inhomogeneous differential equation because of the term sin x. Then the next differential equation, d square y upon dx square plus 3y square dy by dx is equal to 0. Here dependent variable and their derivative present in each term. Therefore, this is homogeneous differential equation. But because of this product term, it is non-linear. This is non-linear but homogeneous because each term contains dependent variable and or its derivative. Therefore, this is homogeneous differential equation. Let us solve one example. Find the degree and order of this equation and also check the linearity and homogeneity of this differential equation. This differential equation involves these fractional terms. Therefore, to find the order of the differential equation, we have to remove the fractional powers. We have to rationalize this equation. For this, remove the fractional power. Therefore, this equation may be written like this, that square root of dy by dx is equal to minus this t square y by dx square plus 3x shifted to right hand side. Then square root of dy by dx is equal to minus t square y upon dx square plus 3x. Square both side. Squaring both side, then we get dy by dx is equal to square of this is first term square plus second term square plus 2 times product of first term and second term. Then we get d square y upon dx square bracket square plus 9x square plus 6x into d square y upon dx square. Or this equation may be written in standard form like this, d square y upon dx square bracket square plus 6x d square y upon dx square plus dy by dx plus 9x square is equal to 0. Then here highest derivative is of second order. Highest derivative in this equation is of second order. Therefore, order of this equation is 2. That order is 2. Then power of the highest derivative is 2. Here the highest derivative is d square y upon dx square. Its power is 2. Therefore, degree of this differential equation is also 2. Order 2, degree 2. Then linearity. Linearity. This equation is non-linear because of this power 2. D square y upon dx square's power is 2. Therefore, this equation is non-linear. And the last, homogeneity. This term, in this first term, the dependent variable derivative is present. Here also dependent variable derivative present. Here dependent variable y's derivative present. But here dependent variable or its derivative is absent. Therefore, this is non-homogeneous or inhomogeneous equation. In this way, in these differential equations, order 2, degree 2, it is non-linear and non-homogeneous differential equation. That's all in this lecture. Thank you.